everyone. I am Master Hans Coding and I'm going to present you a new project that I'm working on. It is called the Ground Station project. This project has several goals. The main goal is to build a system that can listen to amateur satellites. For example, Qubik, Phasma, AcubeSat. There are many other satellites that you can find on the page of Yaru. It is International Amateur Radio Union. I also would like to join the SatNox ground stations network, which was built by the Libre Space Foundation. Here. I also want to learn radio frequency engineering, to learn embedded C programming, and to discover the satellite communication. Before achieving the goal of listening to amateur satellites, which have quite low power signals, I like to first have as current goal to be able to listen the IPRS data packets from the ISS, from the ARIS payload. During this month, October, I did several activities and I will present them to you so that you can provide me some critics or just to share it to others, the adventure. During this month, I did the project setup. I designed the first version of receptor. I bought and assembled the components and I tested the station. So what are the requirements of this ground station? So the APRS signal is 145.8 MHz. It is approximately minus 85 dBi at ground level. It should be portable and I should be able to control it from phone. What is the receptor architecture that I made? So using GPT, my best friend. So there is a Raspberry Pi, a software-defined radio, a low noise amplifier, bandpass filter, antenna. The LNA is not powered by BST, it is powered by a battery, and Raspberry Pi is powered by a battery as well. There is a user interface, which is using the Raspberry Pi Connect tool. So I can use the PC or the phone to connect to control the Raspberry Pi. This architecture is designed to get the IPRS data signal, so 145 MHz. This is what the ground station looks like for now. You can notice the Raspberry Pi here, this software-defined radio dongle here, a coaxial cable, the low noise amplifier powered by a battery, a bandpass filter here, and an antenna. You can see the low noise amplifier here, and I soldered the cable to it. This is the receptor user interface on the PC and on the phone. So the antenna has a 2.15 dB gain. It is designed for amateur radio frequencies. This is the bandpass filter, which contains the 145 MHz frequency. The bandpass filter is used to reduce the noise generated by the other frequencies that are outside this range. Coaxial cable, the low noise amplifier, which is supposed to add 20 dB. One of the portable battery, the Raspberry Pi, another battery, the software-defined radio dongle. And that's it. Those were the components of the ground station for now. And now we'll tell you about the tests that I did to evaluate if the receptor is working and if the LNA is working. So what are the test goals? Check if the LNA is working, evaluate if the ground station can receive signal. So to check if the LNA is working, I will need some tools. The first one is to evaluate the power of the signal to see if the LNA is really adding 20 dB of power. And there is also a tool, I need also a tool to check this, to evaluate the signal to noise ratio at a specific frequency to check if the battery isn't adding noise, to evaluate if the SNR is good enough to be able to listen to signals, to work with signal. So those are the two test tools that I have. One is providing waterfall plots, so frequency, time, and power. Another one is providing the frequency spectrum, so only frequency and power. This other tool is also providing computer calculations to be able to compute the signal to noise ratio. So I did 3 test cases, the LNI powered and unpowered, to see if there is a difference. I also did a signal quality evaluation using the different batteries to see which one is the best. And I also used a GNU radio on the FM band to see if the receptor can receive signals. First, the LNA powered and unpowered. You can see that there is a difference between the two plots, the two waterfall plots. On the right side, there is much more gain, much more power. It is 10 dB more power than when the LNA isn't powered. So we could say that the LNA is working. Let's evaluate now the quality of the batteries, and especially if they add noise. We can see that on the first one, there are some signals that we can see that there are some signals in the waterfall plot. Unfortunately, I shifted the measure. So on the left side is from 148 to 150, and on the right side it's shifted by 0.5 megahertz, and we still see the same noise, the same signals on both plots. So I think it is noise. So this battery isn't usable. There is also the second battery. We see that there is a noise pattern here. Every 0.15 or something, there is a noise. And even if we shift the measure, we still see the same noise pattern. Finally, the Energizer battery seems the best because it doesn't seem that there are some noise on the plots. So the Energizer battery is the most suitable battery that I have. Let's evaluate the signal to noise ratio now. So I used the signal at 150, even if it might be too optimistic. And the signal to noise ratio computed is 51 dB. And I used 111 pins. So we can say that it is a very good signal to noise ratio, but maybe this isn't a signal, maybe it is only a noise. But it is a first step. And finally, the GNU radio on FM band tests. I use the GQRX software to be able to control the dongle and listen to FM radio, and this was a success. So the receptor can receive signals. To conclude, this month I did the project setup. I built several tools to evaluate the quality of signal and to evaluate the power. And I can say that the receptor can receive signal, so it will probably work with IPRS signals. What would be the next step the next goals for the coming month. I will need a tool to evaluate the noise level in watts, so that I can evaluate if the receptor can receive the APRS signal. And we'll also start the activity of getting the APRS data from ISS. Thank you for your attention and see you next month.